Hi guys, this is Mrs. Holman, and this is the Census Lecture for Anatomy 1 here at York Suburban. If you're one of my students, you should already have the access to this PowerPoint. If you'd like access, feel free to leave a comment. So we're going to get started today. Specifically, we're going to be talking about the senses and how they integrate with the central nervous system. That kind of rounds out our unit on the nervous system, since we've already talked about the brain and the functions of the brain. So we're going to get started there. First thing to realize is that the way that we define a sense in anatomy is anytime that we have receptors, or what we call sensory receptors, that will send impulses that we now know are called action potentials to the brain. So we classify our senses into 5 different categories. So we have hearing, sight, we have chemical receptors for smell, and we have touch, all right? So let's go through each one of these, and then we have taste as well. Let's go through each one of these together. All right, although we have 5 different senses, we actually only have 3 different types or categories of sensory receptor neurons. So these are all examples of neurons that have specific endings that are going to pick up on stimuli in our outside world that will transmit that stimuli to our central nervous system, to our brain, for us to receive that action potential and to decide what that sense is trying to communicate. So the 3 different categories that we have of sensory receptors are photoreceptors, which means they only pick up light, so you have a pretty good idea of what that sense is going to correspond with. Then we have mechanoreceptors. What is mechanoreceptors? Well, if you think about mechanical, that's usually when you are physically moving something. So if you're a mechanical engineer, you are engineering moving parts for machines, or you're engineering like an assembly line. So something that has to do with physical movement. And then the third part is a chemoreceptor. And of course, you know, biologists are not creative when we name things. That chemo means chemical. So these are receptors that react to specific chemicals. So if you look at this diagram, you can see that photoreceptors are going to be in charge of vision. And we'll talk about the 2 types of photoreceptors we have. Then hearing and touch are both going to be controlled by mechanoreceptors. So they're going to physically be moved, and that movement is going to transmit an impulse or an action potential to our brain. And the last one, our smell and our taste, are both examples of chemoreceptors. So both smell and taste, we will register specific chemicals in our outside environment, and that will send an action potential to our brain. All right, so we're going to start just by talking about photoreceptors. So this, of course, would be the sense of vision or sight. So you guys probably have heard of these terms before, rod and cone. So these are 2 different types of photoreceptors, and you can see kind of where they got their names from. The cone photoreceptor actually has a physical shape difference than the rod, and because of that, that's why we call one cone and one rod. I like the way they name them because I remember that the C for cone stands for color. And that's because the rods are in charge of really just monitoring and sensing how much light is in an area, whereas the cones are really good at sensing the visible spectrum of electromagnetic energy, so they can differentiate between color. And of course, we have different types of cones that will allow us to see the different spectrums of wavelengths. So the ability to see certain colors is really genetically controlled because we have genes that will code for the cones, and the cones will tell us the color. So that's the reason why certain people might be genetically colorblind. Maybe they'll be colorblind, red-green colorblind, and that would be a genetic trait that then manifests in the cones of our eyes, and therefore we can't see that color. So when we look at the anatomy of an eye, we will be dissecting an eye, which is pretty cool. So we'll dive a little bit more into the specific anatomy parts, but right now what I wanted to go through is kind of walk you through just our major players. So you won't need to know all of the different names on this slide, but I'm going to walk you through some of the ones you really should know. So I'm going to start at the anterior surface of our eye, as if this is where light is passing through. So the very first thing that light is going to pass through is going to be a thin membrane called our cornea. And the cornea is a rather flexible tissue that's going to create a space between the cornea and the next layer. So the next layer we're looking at right here is actually the pigmented layer. And this layer is going to be the surface of the iris. All right, and the iris is actually a muscle, or at least is controlled by a muscle. And while it does have pigmentation that's deposited on the surface that gives your eye the different color that it is, the muscle can actually expand or contract based on where it is attached to the outside part of the muscle, of the outside part of the eye. And that's what allows your pupil to dilate or constrict. So dilate means that that pupil gets bigger, and constrict means that that pupil gets smaller. So that's part of how we're able to maintain the homeostasis of how much light can hit our eye. So after the light goes through the cornea, goes through the pupil part of the iris, it's going to come to the next portion of the eye, which is called the lens. And the lens really should be a very round, circular portion of the eye. But part of the purpose of this lens is just like the lens that you might have learned about in your physics class, is that lens that are concave and convex will bend or refract light. So the reason why we need that lens is that we need to be able to concentrate all of the light that is entering our eye, and we need to be able to reflect that image to the back part of our eye, okay? So if the light keeps going through our lens, it will eventually strike the back part of our eye. And the portion that we focus on is called the retina. You might have heard of that term before. The retina is going to be the tissue where the rods and the cones live. So that's going to be part of the nervous system tissue that enters the eye, and that's going to be where the rods and cones are. So a couple things about the retina. Anytime that light passes through your eye, it's going to strike different angles of the retina. So if you are kind of seeing light from the ground, it's going to bounce through your pupil, go through your lens, and it's going to strike up here. If you're seeing light from above, so maybe the sun is shining, it's going to pass through your eye, it's going to strike the retina from below. But if you think about the way that we as mammals adapted, whenever we hear a loud noise or whenever we're trying to look at something and we're trying to really focus on it, we always look at that object head on. And that's because the concentration of rods and cones are really at their maximum in this area here. So we see the maximum amount of detail if we look at something head on. Something else really fun that you can do at home even is you can test whether or not you can see color in your periphery. And remember that we have rods and we have cones. Cones are the ones that see color. What we know now is that we actually don't have very many cones in this area of our eye. All right, so in any area other than this main concentrated area, we actually don't have as many cones. So the cool thing is if you have a friend, and you'd have to get help for this, so I have two different colored pens here. I have a purple pen and I have a blue pen. So if you get a friend to kind of behind your back, switch these pens around so that you have no idea what color it is. And if you have them hold this pen behind your head and then gradually move it, you have to let them know the very first instant, staring straight ahead, that you happen to see this pen in your periphery. You can't cheat. You can't move your eyes to look at the pen. Keep your eyes going straight forward, and eventually you'll notice that the pen is in your peripheral vision. And the test that you do is whether or not you can see the color of the pen. You make a guess. And we always think that we see color in our full range of vision, but reality is that we really only see color more out in front of us. And our peripheral vision is really just light and dark. And that's pretty important because as prey animals, we need to make sure that if there were to be a saber-toothed tiger jumping out at us from our peripheral vision, we need to see movement and we need to see light and dark less than we need to see what color that tiger is that's jumping out at us. So that's kind of the distribution of the rods and the cones. All right, two other things I'll point out, because when we dissect, you'll see these two different types, or these two different anatomical features, and these are called the humors. So humors in anatomy is anytime there's kind of like a liquid matrix. So way back when, a fun fact is, we used to call any liquid in our body the humerus. So they used to think that the humerus is part of the body. So the humor is going to be any kind of like liquid congregation of area. So the very first humor we have is here, so the space between our cornea and our iris. And then the second one, the vitreous humerus, is going to be here. So Why is that important? If you very gently and with a clean hand put your finger on the tip of your eye, and then you kind of move your eyes in two different directions, you'll notice that your eyeball is not completely smooth, that there's kind of a bump on the front of it, and that bump is going to be your cornea. What actually keeps your cornea inflated is that humerus sitting right behind it. So what you can do is, again, very gently and with a clean hand, very, very gently, you can actually put a little bit of pressure on there, and you can feel that the very front part of your cornea is a little bit squishy, and that's because it's filled with fluid. The eyeball in general, too, is also under pressure. So there's fluid inside of that eyeball. And you'll realize this because when we dissect in class, there's a moment where in order to get to the back part of the retina, we have to puncture that humerus, and there's a little bit of oozing, and you can definitely see that liquid comes out of it. All right, I have a fun story about getting some eye in my eye. The one time we dissected without safety glasses, and I got cat eye in my eye when the vitreous humerus popped. So that's a story for another time. One last thing while we're here, we should talk about this thing called the blind spot. So there is a spot in our eye where all of the nerves that are collecting those senses, so all the nerves from the rods and the cone are collecting all of that input, but those nerves and the blood vessels that supply the eye have to exit through an area. So this is the spot in the eye where the optic nerve exits. And it just so happens because we have to have that area for it to exit, it means that there can't be any rods and cones in this small little area right here. So what that means is that every human actually has a perfect blind spot in their vision. Now, I'm sure that if you're out and about in your daily life and you look in a specific area, you don't suddenly go blind. Our brain is able to compensate by the lack for the lack of rods and cones in that area by basically melding together the other images and the other input from the other rods and cones in the direct vicinity. So no worries, you're not going to suddenly, be driving and look in a direction and not see anything. I know you were all worried about that. Okay, so again, we're going to do a lot of these visible body exercises in class, so don't worry about those quite yet. So let's move on from our photoreceptors. Let's move on to our mechanoreceptors. So again, mechanical means movement, or that these receptors are physically touched, and that's how they are able to then gather the input and move that action potential towards our central nervous system. So the two that we're going to go over are going to be hearing and touch. Let's first talk about the mechanoreceptors in our skin. So these mechanoreceptors are going to be buried at different layers of our skin. So let's do a real quick review because we have not learned the integumentary system yet, which is the outer covering of our body and the skin. Our integumentary system is made up of a couple different layers. We can see two of those layers here. So anything that is on the very surface of our skin is known as our epidermis. And remember that that prefix epi means top or surface. Okay. So of course, this is going to be the surface most part of our skin. So you can kind of see this picture, it's cross section dividing somebody's skin. Beneath the epidermis is just the plain dermis. And this is where the majority of our mechanoreceptors are going to be. The thing that's not mentioned here that we do talk about some other times in this class is that the layer of skin beneath this picture is called the hypodermis. And this might sound familiar if you've ever heard the term hypodermic needle. Hypodermic needles are needles that are able to inject medicine into the bottom part of your skin. So it gets through the epidermis, the dermis, and it goes straight into the hypodermis, which is important because that's where the majority of our blood vessels are. And typically if they're delivering medication intravenously, or if they want to give a hypodermic shot, they want to get it straight to the blood. All right, straight to the circulatory system. So what we see here is, first of all, let's just talk about this gnarly piece of hair coming out of our skin. So this would be a hair follicle, all right, or where that hair is able to break through the surface of our skin. We can see that there's a nice little receptor down here. So that's what allows us to actually feel like, even though your hair is dead, it's not living, if you rustle your hair, or if you maybe brush up against something and your little hairs on your arms touch there, you do have receptors attached to those hairs, so you can feel that movement. If you happen to have gotten bit by a radioactive spider and you're Spider-Man, I would expect that those mechanoreceptors around your hairs would help contribute to that thing that we call spidey sense. But that's just a hypothesis. Our other mechanoreceptors are buried either in the epidermis, but most of them are in the dermis. All right, so we can see that there's a couple different types here. So we have these that are going to be, oh, here we go. Let me draw my screen. So we have these that are called Messener's corpuscles, and these are going to be, these are going to help with a certain type of touch. We have these, all right, that are called Merkel discs. And we also have just rough endings. We have Ruffini endings, and we have nerve endings as well. So we're going to go through what each of those do. Okay, so how do those mechanical receptors actually work? So these mechanical receptors will help by essentially, or these are talking about the ones in the ear, sorry. The mechanoreceptors in the ear work similar to the ones in touch in that, the ones that help with touch in that whenever the mechanoreceptors are triggered by either touch or vibration or by heat or pain, those receptors will send that signal to the central nervous system. So how does that work in our ear? How do we get from sound waves to physically moving something in a receptor? So in our ears, we have these tiny little cells, we'll talk about in a second, and those tiny little cells have these hairs, all right? These hairs that stick straight off of these cells in a normal resting potential when we're not hearing anything would be straight up and down. However, whenever there is sound waves, those sound waves will actually affect those hairs and they will bend them one way or another, all right? So basically, whenever we hear something, that sound is going to bend or move the hairs in our ears, which is then going to translate into sound. So how do we translate that into sound? How do we go from moving a hair to hearing different pitches and different noises and different volumes of sound? So in order to understand that, we need to understand the anatomy of the ear. So there are three parts of the ear that you guys are responsible for: outer, middle, and inner. I'm sure you can figure out which one's which. So let's start with the outer ear, and let's go through a couple of those anatomical features that you're going to need to know. The first feature is the earlobe, and that is pretty self-explanatory. So the earlobe is completely superficial. It stops as soon as it attaches to the skin and the skull. And the earlobe does not have any bones to it. So there is just a little bit of cartilage on the outside part of the ear. You'll notice that the lobe itself, the part that actually hangs down, does not have any cartilage. That's the reason why piercing your earlobe is a little less painful. We then, of course, have this structure, which we already learned about, the external auditory meatus, which just basically means ear hole or ear canal. So that moves us into the middle ear. So as soon as we leave that superficial surface, we move into the middle ear, which is deep to the outer ear. So the first thing you should know is this thing called the tympanic membrane, which is the true anatomical term for the term eardrum. And that's going to be right here. So this tympanic membrane is basically going to amplify any sound that's coming into your ear. It's going to gather those sound waves and it's going to transmit them through a series of three bones: the malleus, the incus, and the stapes. All right. You might have heard that these bones also go by another name. So these are called our ossicles. Our ossicles. Each of them also has kind of like a slang name. So the malleus is known as the hammer. And if you look at this shape right here for the malleus, it does kind of look like a really kind of rudimentary club, all right? Then we have the incus, and then we have the stapes. The incus is going to be what's known as the anvil. So if you think about what does a blacksmith's hammer hit, it hits the anvil. And that's going to be this part right here. It doesn't really look like an anvil, but it's the surface that the hammer hits. And then lastly is the stapes, and the common term for this is the stirrup. All right, and I think this one really looks like that. So if you look at that sideways, that kind of looks like a stirrup that you would have if you rode a horse. All right, so those are our three inner ear ossicles, and those bones essentially what they're going to try to do is they are going to transmit any sound that comes into the tympanic membrane directly to the neck structure, which is located in our inner ear, which is the cochlea. So you can see here's the malleus, here's the incus, here's the stapes, And that stapes is going to connect with the cochlea. So the cochlea, we're going to talk about in just a second, is going to be the physical part that helps us distinguish pitch and volume. So the cochlea is going to connect to our central nervous system via the cochlear nerve. So that's going to be here, and then this is going to go off to the brain. Okay. We also have these things called semicircular canals. Those are these little loop-de-doos. All right, and you can see they're kind of convoluted, kind of like one of those puzzles where the rings all loop together and you can't really get them out from each other because they're all intertwined. That's kind of like our semicircular canals. Those semicircular canals are going to be in charge of stabilization. So we'll talk about the semicircular canals and also these other two parts that help us determine whether or not our head is tilted to the side or it's straight up and down, or if you've ever been on a merry-go-round and you've twisted and twisted and turned and turned and turned, and then you get off the merry-go-round and you feel like your world is still twisting and turning, that is due to your semicircular canal. So we'll talk about that in a moment. And then your vestibular nerve is going to be the nerve that is superior to your cochlear nerve, but notice that it's going to gather signals from those semicircular canals. So whereas your cochlear nerve is really transmitting signals that have to do with the pitch and the frequency of the sound, the vestibular nerve is taking messages to your brain about your movement and about the position of your head. So let's dive into what's actually going to be in the inner surface of your cochlea. All right, so in your cochlea, it kind of looks like a snail shell that is all kind of wound up. Your cochlea is going to have these little mechanoreceptors in the inner part of it. And the cochlea is mostly surrounded by fluid, but on the outside part of it, you have these little hairs, and each of these hair cells will have these little cilia that are sticking up from it. And anytime that they are struck or influenced by a sound wave, they will bend. They are then going to connect to the central nervous system and transmit that sound. Okay, so here's another way of looking at it from the profile perspective. When sound hits your ear, it's going to be transmitted in a wave. We know that sound comes in waves. That wave is going to affect the tympanic membrane. So if this kind of moves, kind of like whenever you have seen like a big stereo system and the subwoofer goes, you can actually see that subwoofer move in and out. That's kind of how our tympanic membrane works. That movement on the tympanic membrane is going to move first the malleus, then the incus, then the stapes, and then that's going to connect to this part of the cochlea. All right. The cochlea is then going to send that message up into the brain. Okay. So let's dive into a little more detail. So how does the cochlea distinguish one frequency from another? So the frequency of the pitch from one another. So let's say that we have a really high frequency sound. So let's say our sound is like this, as opposed to a really low frequency sound. All right. The way that this works is that the amplitude of that sound wave, so if we remember from physics class, the amplitude is how high the wave goes. So this would be the amplitude. If the amplitude increases, it's going to not go as far into the cochlea. If we have a small amplitude, then it's going to go higher, or it's going to go further into the cochlea. So let's look at this image over here. So high frequency waves are going to be stopped at whatever distance they can get through. So the cochlea, if you notice, kind of looks like this snail shell that's kind of wound up here. And you can notice that it is wider at the base and it's very skinny here at the tip. And what that means is that our high frequency noises are going to be able to get stopped early on. All right. So that's how we determine those high frequency sounds. If we have a medium frequency sound, that sound wave might get the whole way to here before it gets muffled and stopped. If we have a really low frequency sound, it might get the whole way through our cochlea, the whole way to the end here. So that's what allows us to determine between the different frequencies of what we hear. It helps us distinguish those frequencies. Now, it's important for me to know, because I'm an anatomy teacher, that y'all's generation is really kind of messing yourselves up in terms of long-term hearing, because one major invention has come about in the past 20 years that is going to affect your generation's hearing more so than anybody else's. Because if you think about the 1990s and you think about what headphones look like in the 1990s. They look like freaking earmuffs, right? They sat on the outside of your ears. They usually had foam around the corners, and we're thinking like straight up 90s regalia. Like they're really dorky looking, right? However, in the 2000s, in the 2010s, we invented these bugger things called earbuds. And while they may look really cool, they go directly into your ear and they have way too much sound. They have way too high decibel sounds. So because we are now injecting that sound directly into our ear, is closer to that tympanic membrane, and we're getting higher doses of the decibel levels of the sound, what we're seeing is that your generation and anybody who uses earbuds is experiencing we're talking a drastically higher level of hearing loss than other generations. So here's how we would break it down. Hearing loss actually happens when those teeny tiny little hairs, so those hair cells, those cilia on those hair cells get snapped off. So if we bend them so violently because we're listening to such a high volume of sound, we'll actually snap those cilia off. And once those cilia snap off, you really can't regrow them. So once hearing loss happens, it's really hard to regain that loss again. So let's talk about how long and how loud do you need to listen to your music in order to get hearing loss, right? And it has to do with the sound, but it also has to do with how long do you have those earbuds shoved into your ear hole, right? So here's the deal. At 95 decibel levels, hearing loss will occur if you listen to at least 4 hours of earbud volume a day. So 95 decibels, by the way, is about the low range of what you can hear in your earbuds. If you look down here at this little asterisk, most earbuds will produce sound in a range of 95 to 108. So think about your AirPod or your earbuds and bumping the volume so far down that you can just kind of barely hear the music. That's 95 decibels. And that means that if you listen to your music that low for 4 hours, you're getting hearing damage. Bump that up 5 decibel levels, 100 decibel levels. So now we're kind of at the mid-range of what your AirPods can do, or your earbuds, whatever you call them, of what they can do. If you listen to 2 hours of music at that decibel level, you're experiencing hearing loss. But I know you guys, and I've taught in the school long enough to know that when they're walking down the high school hallways, you are not listening to it at medium level. Everybody has their earbuds cranked up as high as it can possibly go. And that is about at 110 decibels, right? So the 108, 110 range is about the highest that you can listen to your music at with the earbuds that go into your ears. That means that if you listen at that level for at least 30 minutes a day, and let's be honest, y'all listen to at least that much, probably way more, you're getting hearing damage. And most of the time, it's an every day you're listening to that much. So you are incurring hearing damage. Let's kind of go to the range of going to like a loud outdoor or indoor concert. If you go to a concert and you have those huge, huge speakers, like that's the fun place to be, right up in front by the speakers. But if you leave that concert and your ears are ringing, you have experienced hearing loss. And if you do that perpetually and you do that enough times in your lifetime, you will not notice it right now. You will be A-okay and you will continue to go to concerts. You won't notice it until you're older. And then you're going to be spending the rest of your life going, huh? What'd you say? Can you say that louder? Can you repeat that, please? Because the hearing loss that you incur right now is going to manifest later in your life. So y'all look really cool with your earbuds in your ears. You look really cool going to concerts, but you're not going to look really cool as 35-year-olds who are going deaf. So think about that and perhaps lower the freaking volume of your earbuds and save yourself a little future humiliation. So that is my PSA for today, and I'm going to move on now. The other part of your ear that we mentioned are these things called the semicircular canals. So these are going to be parts of your ear that help with equilibrium in addition to hearing. So the parts that have to do with hearing really are just the cochlea, oops, let's back up, the cochlea and the cochlear nerve. So this part really has to do, goodness gracious. Here we go. This part really has to do with hearing. anything north of that or anything inferior to that is going to be really in charge of equilibrium. So we have these two structures here called the utricle and the saccule. These two structures here are in charge of our equilibrium when we are standing. So this is non-movement equilibrium. So this would be like staying balanced if you are standing still. So a really good example of this would be like if you do yoga and you try to do the tree pose, or if you try to do eagle and you fall over a little bit. That's going to be challenging these two parts of your inner ear. The other part of your ear that helps with balance and equilibrium are called your semicircular canals. So you can see these system of loops that kind of go through each other on a bunch of different axes. These loops are going to be what help you maintain balance if you are moving. So if you've ever been on a merry-go-round, we talked about this before, and you spin, you spin, you spin, you get off, you still feel like you're spinning. Because through all of these parts of your ear, they're filled with fluid. And if you've ever like stirred a glass of water with ice in it, and you stir and you stir and you stir, and then you let the cup go straight and you don't stir anymore, the water on the inside will continue moving. So liquids will continue with inertia and they will continue to move. So if you're moving on a merry-go-round, the fluid in your semicircular canals start to move with your motion. When you stop, the fluid doesn't stop. So that movement of the fluid inside of your ear is going to be what gives you that really off balance, that crazy feeling after getting off of a merry-go-round or a roller coaster where you feel a little off balance and a little off kilter. So that's going to be how we establish equilibrium. All right. Now, those are the movement equilibriums. The utricle and the saccule are going to help us if we just are tilting one way or another. So if you hang upside down for a really long time, your utricle and your saccule will start to adjust to that. And that's because of the force of gravity on the little hairs inside of the utricle and saccule. And the semicircular canals, we kind of already mentioned this, will continue the movement of the fluid inside of there even after you've moved. So if you rotate around in a circle, that fluid will move inside of those canals. And then when you stop moving, it will continue to move, which is what gives you that, that effect of being dizzy. So the last type of receptors we're going to talk about correspond to smell and taste, and these are the chemoreceptors. So these are going to react to the shape of the chemicals that physically land in a receptor. So remember, any other time we've talked about receptors in anatomy, typically if we have a cell, on the outside of the cell, that cell will have receptors. So here's our cell, and here's the receptor on the outside of our cell. And we've kind of always come back to this idea that a receptor has a certain shape, and whatever the chemical is, that chemical will fit into that receptor based on the shape. So if we have a receptor that looks like this, and it looks like a circle, that chemical will probably be circular in shape, right? So we have the chemical, but then we have the receptor that it corresponds with. So when we talk about our olfaction, so this is our smell, they are chemoreceptors. And in this bottom, or in the top part of our nasal passage, we have a very thin membrane that separates the top part of our nasal canal and our olfactory bulb. And if you guys have already done your sheep dissection, we would have talked about already the olfactory bulb in sheep and how it's much larger than in humans. But in our olfactory bulb, this is going to be where all of the neurons are that will continue that signal or that action potential up into our cerebrum or up into our brain. So we can see there are these nerve fibers that stretch in between that space, and here's where we're going to be talking about. Here are these little receptors or those supporting cells that gather that scent, that gather that smell. Okay, so when we talk about the smell, and we look at these individual cells, these olfactory neurons, they're actually going to span the width of the distance between the inner part of our nasal canal. So this would be like if you would stick your finger way up your nose, it would land right here. And then this would be our olfactory bulb that goes to the brain. So these cells, you can see, will stretch from our olfactory bulb to the bottom part of our nasal canal. And these cells are pretty special because on this side, they have these dendrites that are suspended in this mucus. Yes, that's right. We're talking about the boogers. So the mucus that is inside of your nose serves a really important purpose. That mucus is to first trap any type of pathogen that's trying to get into your respiratory tract. So it's going to trap dust, it's going to trap little tiny bacteria, viruses. So it's important that we have that mucus there to stop that those pathogens from getting into our respiratory tract. The second thing that it does is that it traps things that we're smelling. So if little tiny chemicals are coming in through our nose, those chemicals will get stuck in the mucus and they will be taken to the dendrites of those sensory neurons. As soon as they land on that neuron, the impulse or the action potential will transmit through this neuron, go through our olfactory bulb, and then eventually to our brain. Okay. Now, when we talk about the actual smells that you're smelling, there's a huge profile that the human nose is able to receive. And remember that the chemicals that we're actually smelling have different shapes. So these are different examples of what we call odorants. All right, so that would be like different odors. So everything that you smell is a chemical that came from whatever it is that you're smelling. So I always like to remind students now to kind of gross them out that if you go into the bathroom after somebody else has been there and maybe they were getting rid of waste, and you walk into the bathroom and you smell that, just remember that you smelling that waste is actually because tiny little parts of fecal matter are lodging themselves in your nose, being sent to these neurons that are inside of your nasal canal. They land there, and that's why you smell that not so nice smell. So just remember, if you smell it, there's literally poo in your nose. So those odorants are going to land in very specific receptors. What makes smell so complicated and so really fun to study is that different sides of a chemical can stimulate different types of receptors. So you can see at this first example, I think it looks like an upside down umbrella. The very base of the umbrella can land in this receptor and trigger that, or it can land in this receptor because the opposite side of it also has that shape. So that's the reason why you hear of these things called like a chemical profile or like a flavor profile. It has to do with those complex receptors that those chemicals might land in. There are also smells that will trigger the same receptors. So this graph over to the right tells you how certain odorants, certain smells, or certain chemicals will actually trigger the same receptors even though they are different chemicals. So it is very much not that we have one receptor for every smell in the world. It's that any chemical that comes into our nose can trigger any number of receptors, and the combination of those receptors are what actually give us that well-rounded smell. Now, we also know that there's this thing called olfactory fatigue, and I'm sure you guys have experienced this, especially early on in the year. If you had my class, we work with vinegar a lot in my bio classes. So a lot of times when we do labs with vinegar, students walk into my room and they're like, oh, gross, it smells like vinegar in here. But the reality is your brain is pretty smart. And as you experience a sense, once your brain has kind of figured out what that scent is, it starts to make note of it less and less and less. So what that means is that scents that are really, really strong typically will start to become less obvious. They will actually decrease in their intensity over time. So if you want to go into a really, really cool science position, you'll go into the perfume industry as a chemist, because there are chemists that work in perfume industries that will make and manufacture perfumes that have fragrances that change over time. So the most expensive perfumes you can get, or the most expensive colognes you can get, are scents that when you put them on your skin, different times where you smell them, they'll actually smell different. And what that means is that your brain will constantly be smelling them, which gives it the appearance that they're going to last longer on your skin. We've all been through that phase in like middle school where you get like those really disgusting body sprays. No offense if you like them, but I can't stand them anymore. Where you spray them once and it just like takes over the whole room. But then really 20 minutes later, you can't really smell them. Those are the less expensive scents because they have a very distinct profile. Your brain will kind of fade out those scents after a while, whereas the more complicated, more expensive perfumes will change, which will overcome this thing that we call olfactory fatigue. Okay. Now, I wanted to speak a little bit about how we process these smells that come through our come through our brain. So we talked about how we physically get the smell into our receptors, but let's talk about where it goes after that. And for right now, what I'd like you to think of is a specific smell that you attach to your childhood, or maybe like a real emotional connection you have to a smell. And I'll share an example of mine. The first smell that I have, don't make fun of me, it's nerdy, is that the YS Science Wing has a smell. And I don't know if you've ever noticed it, but every summer when I come into the room, into my classroom, and I haven't been there for a while, I'll open my classroom door or the doors to the science hallway, and it just makes me smile because I remember the first year going into my classroom and being so excited to be a teacher. And that smell reminds me of teaching, and it reminds me of being in my classroom, my safe space, and having fun in my classroom. So that smell makes me have an emotional reaction. Another example is I can still to this day remember the perfume that my grandmother wore. And even though I haven't smelled that in years, every now and then I'll be passing people in a crowded place and I'll get a whiff of that perfume and I will instantly think of my grandma. And that's because our sense of smell actually travels through this part of our brain called our limbic system. And our limbic system really is the center of where all of our emotions lie. So in the progression of that smell receptor's action potential to our brain, it passes through our limbic system, which explains why so many of us have these emotional attachments to smell. And for some of you guys, it might be the smell of a loved one. For some of you guys, it might be the smell of your room or your house, or maybe like a freshly baked cookies. I don't know. So this leads us to our very last sense that we're going to go over, and that is gustation. So that's the sense of taste. Taste is definitely a chemoreceptor, which kind of makes sense because you're eating food, you're digesting the food, and the small molecules that make up that food are chemicals. So the way that we taste is we have on the surface of our skin, we have these things called taste buds. Those taste buds are going to be our receptors, and those receptors are going to transmit that signal to sensory nerve fibers that go into, that will travel up into our brain. So the actual taste buds themselves are actually inside of this structure called a papillae. And the papillae are going to kind of play a really fun role in taste. So although we know that taste is a chemoreceptor, we still don't know exactly how it is that that taste signal is transmitted to our brain. So there's kind of like 3 different theories right now, and it's really hard to prove which one is which. So let's go through these theories. The first theory is that for every different type of taste, so we know there's 5 different tastes. There's bitter, there's salty, there's sweet, there's umami, which is that kind of savory taste, and then there's sour. So the one theory is that the different parts that make up each papillae, each little cell would have a separate scent, would have a separate taste. So this would be one taste bud, and it would be filled with a cell of each different taste. So whichever of these is triggered by that chemical that we eat would transmit to our brain that is going to be what taste it is. The other leading theory is that the taste bud itself is made up of a bunch of generic cells, but inside of those cells are different arrangements of those different tastes, right? So you can see these different spots inside of them. So basically the combination of those that would receive those signals would trigger that response and be taken to the brain. And then the last idea is that even though all of the cells within the taste bud would receive a different type of taste, that all of those would kind of neutrally be intermingled and taken to the brain separately. So we're not exactly sure which of these theories is true, but there's still a lot of research to be done on taste. All right. So this is a video that I linked in here. I'm not going to have you watch this now with a screencast because we're going to be doing a lab. Basically, this is your reminder. Make sure that you have food coloring somewhere because we're going to be doing a lab very, very shortly on how it is that we can determine whether or not you are this thing called a super taster. So if you've heard about this term super tasters, there are some people in the world that are really foodies, that when they go to like a cheese tasting or they go to a restaurant, they like the best of the best. They really like good food. And they actually have the ability to taste more than other people. So there are super tasters and there are sub tasters. And really what it comes down to is the number of papillae they have on their tongue. And this is a genetic thing. So just how many you develop as you grow in the womb will determine whether or not you have a better or a worse tasting ability. So the lab that we're going to do is basically going to have you guys stain your tongues blue. And the cool part is that the dye, specifically in blue food coloring, stains the tissue on your tongue, all but the papillae. The papillae will not stain with the blue food coloring. It has something to do with the chemical inside of blue food coloring. So what we're going to do is I'm going to have you guys swish blue food coloring around in your mouth. It's going to make you look like you're a Smurf. And then you spit it out, and then you look on your tongue, and you count how many papillae are in the area of a hole punch. So this is my family, my poor loving family. When I first introduced this lab, the first year I taught anatomy, I was like, guys, I need to do this lab with you guys before I do it with my students. So I made them practice. And so this is my picture of my family and then me and my husband practicing this so that I could have them do the trial run before I ran out with you guys. So basically what it's going to look like is the surface of your tongue is going to look like it has these little white spots on it. And that's because those are the little papillae. Remember, your taste buds are inside of those papillae. And if you have a certain threshold of papillae in one area, you are a super taster. If you have very few, you are a sub taster. So we're going to do that in class, and we'll try to determine if anybody is a super taster. So the last thing I want to leave you with, and this is part of the screencast, so if you're working on handwriting your notes and then processing your notes, make sure that you include this video as part of it. As I'm going to have you watch the Bozeman video called The Senses. And I'm going to link it on the daily class planner beneath this screencast. If you have the PowerPoint for this presentation, it's also embedded in the PowerPoint. This is our very favorite Bozeman, and he goes through and does a really nice explanation of the senses. All right, so that's going to wrap us up for today. I hope that all of that information was helpful, and I will see you in class.